The helmet presses against the glass of a drifting gas cloud. Silence, everyone assumes, is waiting on the other side. That assumption is about to break. You've been told this your whole life. Space is silent. No air, no sound, no exceptions. A famous movie tagline built an entire cultural belief around it. In space, no one can hear you scream. It feels like an absolute law, the kind nothing could ever violate. 240 million light-years away, at the center of the Perseus galaxy cluster, astronomers pointed a telescope at exactly this kind of impossible phenomenon. They found something science fiction never prepared you for. A black hole, 240 million light-years away, is playing a real note. You just can't hear it. Not a metaphor, not a translated visualization built for a press release. An actual acoustic pressure wave, physically real, rippling outward through space the same basic way a drumbeat ripples through the air in your room. Sit with that for a second. Sound needs something to travel through. It's not a special kind of energy floating freely on its own. It's a pressure wave, built from particles bumping into each other, compressing and releasing in sequence, carrying the disturbance forward one collision at a time. Air does this. Water does this. A steel beam does this. A true vacuum does none of it, because there's nothing there to bump into anything else. That's why the "space is silent" rule exists in the first place, and why it's correct almost everywhere. The overwhelming majority of the universe is close enough to a perfect vacuum that sound simply has no way to move through it. Between planets, between stars, across most of the emptiness separating galaxies, there aren't enough particles per cubic meter to support a pressure wave of any kind. Scream in that environment, and there's no medium available to carry the sound anywhere, not even the few centimeters to someone floating beside you. But here's the distinction the popular version of this rule quietly skips over. Almost all of space being a vacuum is not the same claim as all of space being a vacuum. Those two statements sound similar. They are not the same physics. In the hearts of massive galaxy clusters, something different is happening. The space between individual galaxies out there isn't empty in the way interstellar space usually is. It's filled with an extremely hot, extremely thin gas. Scientists call the intracluster medium, and in certain regions, that gas is dense enough just barely to support real pressure waves. That's exactly what NASA's Chandra X Ray Observatory detected at the center of the Perseus cluster. Ripples, physically real, moving through the hot gas surrounding the cluster's central supermassive black hole. Genuine sound waves propagating through actual gas, confirmed by direct observation. Here's the open question worth holding on to through the next few minutes. If space is mostly a true vacuum, exactly how dense does a region need to become before sound becomes physically possible again? And if nobody can hear it directly, how did anyone detect a sound wave at all? The instinct almost everyone carries treats sound is impossible in space as an absolute physical law, with zero exceptions anywhere, ever. That instinct comes from decades of accurate science communication about vacuum conditions, reinforced by pop culture repeating the same tagline until it feels like settled fact. It's not wrong about most of space. It's wrong about treating the rule as universal rather than conditional. The Perseus cluster's black hole doesn't break physics by producing sound inside a vacuum. It produces sound because the specific region immediately surrounding it isn't a true vacuum at all. It's a real, if extraordinarily rarefied, gaseous medium, capable of carrying pressure waves the same fundamental way Earth's atmosphere does, just far less efficiently and at a frequency almost impossible to describe using ordinary musical language. Understanding this required scientists to abandon a simple binary model. Vacuum equals silence. Atmosphere equals sound. Nothing in between. Reality doesn't sort itself into two neat categories. Sound propagation depends on the specific particle density of any given region, and that density varies enormously across the universe, from near-perfect vacuum in most places to relatively denser, though still extremely thin, pockets like the cores of galaxy clusters. The gas at the center of the Perseus cluster reaches temperatures of tens of millions of degrees. That number alone sounds like it should make sound propagation harder, not easier, given how thin the gas actually is compared to anything on Earth. But temperature and density aren't the same property. and this particular gas manages to be simultaneously far hotter and far less dense than any sound-carrying medium found anywhere on Earth's surface, while still holding just enough particles to carry a genuine pressure wave. NASA's Chandra X Ray Observatory launched in 1999, and it wasn't built as an audio detector. It has no microphone, no acoustic sensor of any kind. It reads X-rays. So how does an X-ray telescope find a sound wave? The answer is the specific mechanism the title's curiosity gap depends on. Scientists studying Chandra's X-ray images of the Perseus cluster noticed something unusual in the data. Concentric ripple patterns in the hot gas surrounding the black hole, visible as variations in X-ray brightness arranged in expanding rings, radiating outward from the center exactly the way ripples spread outward from a stone dropped into still water. Those rings weren't random noise in the data. They were the direct visual signature of a real pressure wave, moving through the gas, compressing and releasing it in a repeating pattern, exactly the mechanism that defines sound anywhere it occurs. The X-ray brightness varied because the gas itself was being physically compressed and stretched by the passing wave, brighter where compressed, dimmer where relaxed, over and over, in concentric rings stretching outward across a staggering span of space. In September 2003, astrophysicist Steve Allen and colleagues presented exactly this finding at a NASA press conference, using Chandra data to describe those concentric ripples as direct evidence of a genuine acoustic pressure wave. This wasn't an artistic sonification of unrelated data, the kind of stylized space sounds popular astronomy media often produces by converting light curves or radio signals into arbitrary musical tones. This was a real, physically confirmed pressure wave, detected through its actual signature in the gas, not translated or invented for effect. Here's where the scale of the phenomenon becomes almost impossible to hold in your head at once. The sound wave detected in the Perseus cluster has an estimated frequency of roughly 1 oscillation every 10 million years. Convert that into musical terms, and it corresponds to a pitch approximately 57 octaves below middle C. A piano has about 7 octaves total, top to bottom. This note sits 57 octaves beneath the lowest note any instrument on Earth could ever produce. Human hearing covers a range from roughly 20 Hz to 20,000 Hz. That's the entire audible spectrum available to your ears, from the deepest rumble to the highest whistle you can consciously detect. The Perseus cluster's note falls so far below that range that even if you could somehow survive floating in that gas, unprotected, your ears would be biologically incapable of registering the sound as sound at all. Not because it's too faint, because it's too slow, oscillating on a time scale that has nothing to do with what a human eardrum evolved to detect. To make this wave audible to a human audience at all, NASA's Chandra team increased its frequency by a factor of roughly 144 quadrillion. That's not fabricating a sound that wasn't there. That's taking a wave that already genuinely exists and shifting it upward through the frequency spectrum until it lands somewhere your ears can process. The same basic principle as speeding up a slowed-down recording until pitch returns to a recognizable range. This is where the obvious counter-argument surfaces, and it deserves a direct answer rather than a dismissal. Couldn't an astronaut theoretically float in that gas and hear the note directly, given enough patience? Setting aside the impossibility of human survival there, given the extreme radiation, extreme temperature, and gas so thin it behaves almost like a vacuum relative to breathable air, the deeper problem isn't survival at all. It's biology. No human ear, under any circumstances, at any distance, could physically perceive a frequency 57 octaves below its detection threshold. This isn't a limitation of technology or protective equipment. It's a limitation baked into how ears themselves are built to respond to vibration. The wave could be perfectly audible in physical terms, pressure varying exactly the way any sound wave's pressure varies, and it would still pass through a human ear completely undetected, simply because the oscillation happens far too slowly for that biological structure to register it as anything at all. The mechanism producing this wave in the first place traces back to the black hole itself, and this is where the failure chain, if you can call cosmic physics a failure at all, really begins. Supermassive black holes at the centers of galaxy clusters don't sit quietly, doing nothing. They periodically erupt, releasing enormous bursts of energy into the surrounding gas as material falls inward and jets of superheated particles blast outward. Each eruption sends a disturbance rippling through the intracluster medium, compressing the gas immediately around it, then releasing it over and over. Exactly the mechanism that defines a pressure wave anywhere it occurs. Because the black hole's eruptions happen repeatedly, sustained over enormous timescales, the resulting pressure wave isn't a single brief pulse. It's closer to a continuously sustained note, held not for seconds or minutes, the way a musical instrument sustains a tone, but for tens of millions of years, propagating outward through the cluster's gas in expanding rings that Chandra has now captured directly in X-ray light. Each secondary failure in this chain adds a new layer of strangeness. The vacuum-dominated nature of most of space keeps sound almost entirely confined to a handful of exceptional environments. The specific density of the Perseus cluster's gas happens to cross the threshold needed for pressure waves to exist at all, a threshold that would fail in the vast majority of intergalactic space surrounding it. The black hole's own energetic activity supplies the actual disturbance driving the wave forward, without which the gas would sit still despite technically being dense enough to carry sound if disturbed. And the resulting frequency lands so far outside human hearing range that detecting it required an X-ray telescope reading brightness patterns, not any instrument designed to listen for anything at all. That's the specific chain of conditions required for this phenomenon to exist, and it's worth noticing how narrow that chain actually is. Remove any one link, insufficient gas density, no black hole activity, or a different frequency landing inside audible range needing no translation, and the entire phenomenon either wouldn't exist or wouldn't need the elaborate detection method that made it famous. There's a genuine irony sitting at the center of all this. The object most associated in popular imagination with darkness, silence, and total cosmic destruction, a black hole, turns out to be the source of the deepest, oldest, most sustained musical note ever detected anywhere in the known universe. The thing culture treats as the ultimate symbol of nothingness is quietly responsible for one of the most remarkable acoustic phenomena physics has ever confirmed. A useful way to hold this in mind: picture a drum submerged deep underwater compared to a drum out in open air. Both can transmit sound because both have a real physical medium surrounding them, even though water behaves completely differently from air as a medium. The intracluster gas works the same basic way, just as an extraordinarily thin, unbelievably hot version of that same underlying principle. Barely a medium by any everyday standard, but still, technically, undeniably, a medium. Or picture the difference between whispering in an empty concert hall and whispering inside a sealed, genuinely airless chamber. The empty hall still has air filling it, so the whisper carries, however faintly, bouncing off distant walls. The sealed chamber has nothing, so the whisper goes nowhere, vanishing the instant it leaves your mouth. Most of space resembles that sealed, airless chamber. The Perseus cluster's core resembles the nearly empty concert hall, thin as it is, still technically capable of carrying a sound across its expanse. Or think of an impossibly long note held on a massive pipe organ, sustained not for a few seconds, but for tens of millions of years continuously, inside a room so vast that the sound takes hundreds of millions of years just to be observed from outside its walls. That's a reasonably accurate scaled-up description of exactly what's happening at the Perseus cluster's core right now, and has been happening there since long before humans existed to notice it at all. None of this changes the underlying rule that made space is silent a reasonable thing to believe in the first place. Sound propagation is a function of medium density, not some uniform property attached to the single, broad category called space. That principle explains why sound behaves completely differently depending on where in the universe you happen to be looking. True vacuum carries nothing. Thin interstellar gas carries almost nothing. Dense planetary atmospheres, like Earth's, carry sound easily and efficiently. And the superheated intracluster medium at the center of a massive galaxy cluster sits in a strange, narrow middle ground, thin enough to seem impossible, dense enough to carry a real, physical wave across unimaginable distances. This principle will remain true for any future observation of any other galaxy cluster, nebula, or gaseous cosmic structure with sufficient particle density to support acoustic waves, regardless of how advanced observational technology becomes. Future telescopes, more sensitive than Chandra, more precise in their X-ray imaging, are already being planned as part of the next generation of space observatories designed specifically to study hot gas environments like this one in far greater detail. Those future instruments will map more ripples in more clusters with sharper precision than Chandra ever managed. They will not and cannot make that sound audible to an unaided human ear floating anywhere near its source. The limitation was never about instruments or distance. It's built into the frequency itself, sitting 57 octaves below anything a human eardrum could ever register. A note that will keep playing patiently, indifferently, for millions of years yet to come, whether or not anyone out there ever finds a way to actually hear it.